going to start talking about graphing polynomials today. In our notes, we're going to get some different definitions down, some characteristics, and then we will be working on this for the next several sections, talking about how to draw a graph. So in general, if I'm talking about a polynomial, what does a polynomial look like? It is a great question. We have seen some polynomials already. We've factored polynomials. We graphed some basic polynomials. It's basically something like, this is what the formal definition looks like. That's a little confusing to look at. But it's basically decreasing powers of x. So if I gave you, like for example, if I said 5x to the 7th minus 3x to the 4th plus 2x squared minus x plus 3. That's a polynomial. Okay, so a polynomial, poly means many, so you just have a lot of terms added or subtracted. When you're looking at those, your powers are always going to be whole numbers. Okay, your exponents are not going to be negatives, you're not going to have fractions or decimals. So you just have those nice exponents. If I ask you for your degree, that's just the highest power. It may or may not be written first. If it's in standard form, then it will be in order, high to low, but it doesn't have to be. So you just look at each term. The highest exponent you see is your degree. The coefficients are the numbers multiplied with x. A constant is a number without a variable. The leading coefficient is the coefficient of the term with the highest power. And leading term is the term with the highest power. Remember, the terms are the things being separated by addition and subtraction signs. So for instance, if I looked back at this example, what would be the degree in that? 7. You don't have to add them all together, you just take the highest power that we see. My coefficients, those are all the numbers multiplied with x. So my coefficients would be 2 and -1. What is my constant in that example? 3, because that one doesn't have an x with it. The leading coefficient, you have to take the term with the highest power. What's the coefficient of that term? 5. My leading term is that entire term with the highest power, 5x to the 7th. So, things to note about this, when we graph them, it's always smooth and continuous. You're not going to have breaks in the graph. You don't have any corners. Any transformation rules that we learned before still apply. I'm going to go ahead and add in something I already said. All the exponents are whole numbers. So those powers on x have to be like 1, 2, 3, 4, and so on. You can't have negatives, you can't have fractions or decimals for your powers. Any questions there? All right, so first examples we're going to do is just look at some functions and decide if these are polynomials or not. So would this first one be a polynomial? Yes. Okay, what is the degree, the highest power of x? 4. Remember, the degree doesn't have to come first. I also asked, I didn't ask 4, but if I did, what's my leading coefficient? What's the coefficient of that term with highest degree? -3. Good. So just don't assume leading coefficient is always the first number. Things could be flipped around. B, the square root of x. A square root is the same thing as a 1/2 power. Would that be a polynomial? No. The reason is the fraction exponent. C, we said polynomials are nice smooth curves. When we look at the functions, it was just all these powers of x added or subtracted. Would this one be a polynomial then? No, because I'm dividing by x. So your reason, you could give me different things. You could say x is in the denominator. Or you could say dividing by x. You could say dividing is when x is on the bottom, it's like a negative exponent. And we said in a polynomial, the exponents are positive. So lots of different reasons. All right, this one, f of x is equal to 0. I don't have a lot of terms, but does it break any rules? No, so that is a polynomial. The degree on this, it's kind of a weird rule, but if x is 0, we say there is no degree. Degree is your highest power of x, but it's impossible to say if you have a 0, because 0 is the same thing as 0x, or 0x squared, or 0x cubed. You could put any power of x with that, so we just say it has no degree. E, would this one be a polynomial? Yes. My degree, that's like the highest power of x, or another way of saying it is how many x's are in this? Do we have any? No, so this is degree 0. The reason 8 is the same thing as 8 times x to the 0 power. So if it's just a constant, your degree is 0. There are no variables. All right. F. This one's written differently. It's written as multiplication. But let me ask you a question. Could we multiply it out and just have things added or subtracted? Yes. So it is a polynomial. We will look at more of these, but our degree, the degree is the highest power when things are added or subtracted. So to decide the degree here, we have to think about, if I multiply this all out, what would my highest power of x be? Now, I don't really have to multiply everything out. I just have to think about it. I would have an x cubed. In this parentheses, if I square it, I would get an x squared. If you take x cubed times x squared, you get x to what power? The 5th. So my degree would be 5 if we multiplied it all out. Any questions there? next one. You can use a graphing calculator. I want you to take a minute and graph these things. So a very rough sketch is fine. Use a graphing calculator if you want. Just draw me a rough sketch of what these things look like. You might have remembered that one. What's that look like? The chair. Okay, what's x to the 5th look like? A skinny chair. All right, what's x to the 4th look like? And x to the 6th? So why do you think A and B turned out like chairs and C and D turned out like parabolas? What's the difference? Even and odd exponents. Okay, what made it get skinnier? The bigger the exponent. All right, this is something called end behavior. If you just have x to a power, it's going to look like x squared if that power is even, and x cubed if that power is odd. As that exponent gets larger, the graph narrows, or you could say gets skinnier. So that's what we saw on our graphs. Come in. The first two are in. And this was spread on. It's back here on the counter. All right, so end behavior is what happens as x becomes really large or really small. So basically, what direction are the ends of our graph going? And we are not going to be very precise with this. All I'm going to ever ask you to do is draw arrows. Is it going up? Is it going down? That's all I need from you. So it is determined completely by the leading term of the polynomial. So it turns out in a polynomial, all the stuff added on, that changes the middle of the graph. But that first term with the highest power, that's what tells us which direction the ends point. All right, so if it has, let's do an even first. So if it's an even degree. All right, so that's like our x squared, our x to the 4th, x to the 6th. What direction were those ends pointing? Up. So both ends are pointing up. What would happen if I made it a negative x squared? A negative flips it, so they would both be pointing down. All right, if my term has an odd degree, what did it look like if we had x cubed, x to the 5th, x to the 7th? And let's go left to right. So when we were looking at those, it looked like this. So my first one was pointing down, the second one was pointing up. What would happen if we made it a negative x cubed? Right, it flips it over the x and it looks like this. So my end behavior would become up, down. So we're going to take a look at some questions and see if we can decide the end behavior without drawing a graph at all. So if I want my end behavior, the only thing I'm looking at is my leading term. Not necessarily the one that comes first, but the one that has the highest exponent with it. So if I do that, my highest exponent is 4x cubed. Okay, x to the 3rd, that's odd, so I know it looks like a chair. It's a positive 4 in front, so is it flipping? No. So my end behavior is just down, up. I look at this one. What is my leading term? This one right here. Okay, start with your exponent. Exponent is 6. 6 is even, so that means it looks like what? A parabola. There is a negative in front, so what does that do to my parabola? Flips it down. So my end behavior is down, down. Do you guys understand how I'm getting this?
Yeah.
Okay. The next one, it's different because this is in factored form. Okay, to get their end behavior, it has to be all multiplied out. But we only care about the leading coefficient. So we can figure out what the leading coefficient would be without taking the time to actually distribute all this stuff. Because I have a 3, the highest power of x in this parenthesis is just x. In the second parenthesis, I would have an x squared. So if you multiply just that stuff, we would get a 3x cubed. Okay, so that's if we took all the time to multiply every single term, this would be the highest power of x. So what's that in behavior? X cubed. Yeah. X cubed is odd, so it looks like a chair. Positive 3 in front, so it doesn't flip. So down, up. All right, one more. A lot of stuff here, but all I care about is what would my highest exponent be. So we have a 1/2. In the next parenthesis, I would have an x squared. In the next parenthesis, what happens if you take x squared to the third? You get 6. Power to the power, we multiply. In this last parenthesis, we would get x to the 4th. So if you multiply this out now, you add the exponents, so we get an 1/2 x to the 12th. Obviously, that's not the full polynomial, but that's the only part I need. X to the 12th. 12 is even, so what does it look like? Parabola. 1/2 is positive, so it does not flip. So my end behavior? Up, up. All right. Any questions there? I want you guys to take a second and try this next one on your own. Just thinking about end behavior. Match each of these functions with their graph. So f of x, function f, we have an x to the 4th. So what should your end behavior be? It's a positive x to the 4th, so it should be up, up. So that's graph C. I don't know if you labeled it down here or there, but f of x and C go together. All right, G, a negative x to the 6th. It's even, so it's a parabola, but the negative would flip it. So that one is A. All right, this one, 3x cubed. What does that look like? A normal chair. It did not flip. So that is all right, negative 7x to the 7th. So an x to the 7th looks like a chair, but a negative flips it, so that is D. All right, how did we do with this? Good? All right, just a few more things I want to talk about. Some vocab. Not like I'm going to give you a vocab test, but just words that you're going to hear me say, so you need to know what they mean. When I say turning points, it's where the graph changes direction. Okay, so if I'm going up and I'm going down, that turns into a turning point. Or if I'm going down and I switch to going up, that's a turning point. Turning points can also be called extrema. That just means a max or a min. Okay, so there's two types of maximums and minimums. There's absolute and local. Absolute is the highest or lowest on the entire graph. Local is just higher or lower than surrounding points. So it may not be the highest on the graph, but it's higher than the points on both sides of it. Okay, so looking at this, graph F. If I wanted to find and classify the local extreme points, so if I wanted the local max and local min of that graph, what would be the local max on graph F? CD. It's higher than the points on both sides of it. Okay, local min, that's just lower than the surrounding points. You can have more than one. What are my local mins on this graph? Okay, what about on graph G? What's the local max? What's the local min? Okay. Now I want the absolute max and min. For both graphs. So I'm just going to make a little table. Okay. Graph F, does it have a point that is the highest on the entire graph? No, because the ends are going up, so there is none. Does graph F have an absolute min, a point that is lower than every other point on the graph? Yes, what point is that? Okay, we can see this is the lowest the graph ever goes, but we don't have a highest point because it keeps going up forever. Graph G, does that have an absolute max? Mn is here, but does my graph ever go above? It does, because that keeps going up. So do we have a highest? No. Okay, my lowest, this end is going down. So do we have a single lowest point on the graph? No. So we don't have to have maxes and mins. We might, but we might not. We doing okay? Give me like 5 minutes tops. Promise I'm almost done. So those turning points, those turn into the maxes and mins. It's actually related to the degree. So it says if our degree is n, we have at most n minus 1 turning points. That means if my degree is 5, how many turning points could we have? 4. So the number of turning points is 1 less than the degree. Likewise, if you know the number of turning points, the degree has to be at least 1 higher. For instance, if I looked at this graph, how many turning points does this have? 3. So my degree would have to be at least 4. All right. The number of x-intercepts we will talk more about this in the coming days, but it's up to the degree. So if the degree is 3, we could have 3 x-intercepts. If the degree is 7, we could hit the x-axis 7 times. And the last thing, remember with all of our, when we were solving quadratics, I told you we're going to keep track of our multiplicity because it will make a difference later on. This is when it makes a difference. If your multiplicity is odd, the graph goes through the x-intercept. Okay, so what that means is on my graph, if I have an x-intercept of 2, and it doesn't matter if it's 2, multiplicity of 1, 3, 5, my graph is going to hit that point and just keep going. But if you have an even multiplicity, the graph bounces at the x-intercept. So if 2 had a multiplicity of 2 or 4 or 6, what that means is my graph is going to hit it and bounce back the way it came from. So odd multiplicities go through, even multiplicities bounce. All right, any questions?